So I tried to explain the properties of the localization transition, Anderson transition, and to explain, although it's some aspects similar to just a more conventional second-order phase transitions, however, it has many peculiarities, like there is no order parameter in a simple sense. So Stone and Bucket theory, so it's still applicable. And another important remarkable peculiarity is this wave function multifractality, which from the field theoretical point of view means there are infinitely many operators corresponding to modes of wave functions which are RG relevant, and so when you build a big system, the wave function becomes more and more strongly fluctuating. Seen in this new graph. Then I explained the calculation of these exponents to plus epsilon expansion in the sigma model, and I started to tell you this, to complete now about the sort of toy model in which one can understand the properties of this critical points in multifractality, and this is our random mathematics model, which corresponds to one-dimensional system, this hopping, this long-range hopping, such that the hopping amplitude is random, and its typical value is 1/r is distance, and this is in fact a family of such series parameterized by this parameter b, which is the amplitude essentially of this hopping, and then b is large. We can study this. Yeah, and so there is that's a line of fixed points. So this b corresponds to truly marginal coupling from the point of view of field theory, so it's not renormalized. So for every b, there's another theory and another fixed point, and the fact that you are exactly at criticality is that here exactly the power of 2 is 1/r squared, so h squared, average is r squared. If you go away from this power 2, you will go to localization of the localization. Yeah, so at large b, you can study it basically in the same methods of the sigma model. We do conventional theory to plus epsilon dimension, and in the opposite limit, and you get sort of quickly multifractal critical points, because the transition is like 2 plus epsilon, but the transition is in the regime of strongest order of Higgs. Now, at the opposite limit of small b, you get critical points with very strong multifractality, and here, although we can write sigma model, there is no method to treat it. Well, actually, one can, there are now also methods to treat the sigma model, but I will show you a simple way to this regime, namely just real space RG. So it turns out that one can study criticality by real space RG, and I just quickly explain this. It's pretty simple. So basically, you consider you start with the diagonal part of your Hamiltonian, which you just have some diagonal Hamiltonian. At each point, there is some random potential. And then you start, you include in the consideration matrix element with I minus j to 1, which means hopping to the next, to the neighboring side, yeah, from each side to the neighboring side. So most of them are, you can forget about them because the characteristic value of this matrix element is b, it's much larger than unity, and the typical spacing between energies of the unity, so they equivalent to a two-level system, and the distance between energy is much larger than the matrix element, then you only slight relative mixture doesn't make any important contribution. However, with a small probability, this distance between energy levels and the also of b, so these two levels will be close to each other, and then they will be in resonance. Yeah? Then you should consider this two-level system, and you should reorganize it. And then these two sides goes from the mix by this group. Yeah? And so you go to the new eigenfunctions, new eigenenergies, and now new eigenfunctions sit on these two sides. Then you include any consideration matrix elements that you hope on the distance 2, and so forth. Yeah? And so this is a typical logic of real space. Rg, and as a result, you get the evolution equations. So now we can write this procedure in terms of some evolution equation, and it has a structure of the kinetic equation. So in some cases, it turns out that your levels turn out to be in resonance, and then you should reorganize collision. And so that's the logic. The rest is relatively simple math. And by doing this, you find that exactly when this hopping goes like 1 over r, you are at criticality, and your moments of wave function show some power law scaling to the system size. And you find these critical exponents, and the critical exponents and the regular exponents are proportional with parameter b, the small parameter b, times some function of q. So q is the moments that you calculate, and this function q you can just calculate explicitly. Yeah, that's shown here, which is some combination of down functions. Yeah, and this is what is shown here. So when you, so that was the regime of large b, then you have a relatively small amount of rectangularity, so this f of alpha spectrum is relatively narrow, so fluctuations are not so strong, and this the numerics compared to the sigma model calculation, and this is numerics compared to this real space RG calculation in the regime of small b, so this small b here is 0.01, so this blue one is 0.01, and this green is 0.25. And there is a very nice beginning agreement so in this regime with this real space regime. So we have two methods which are complementary, and they match very nicely and describe this family of critical points. And so this is of fractal exponent depends on this fractal exponent with q equal 2 depends on this b. So for small b it's very, very fractal, and for large b it's close to unity, and it's a one-dimensional system, so big rectangularity, and so there's again numerics in 2 invisible curves. So this on this toy model, we see how the mode of rectangularity develops from the regime of weak mode of rectangularity to strong one, and this is qualitatively similar to what happens in Anderson condition in d dimensions when we change the dimensionality, when you go from 2 plus epsilon to high dimensions. At least that's what we expect. Of course, it's only a toy model, so one should not take it sort of the critical point that we have here cannot directly describe some numbers about Anderson transition in d dimensions, but they have sort of similar qualitative features. And in many cases, it's very useful model to test some ideas or some analytical results. Very quickly, a few slides about experimental works on C mode rectangularity. There have been attempts and works with in several settings. I will show you 3 of them. And all of them, I would say, they see qualitatively these non-corrected features. If you start to look at this quantitatively, then it turns out that the spectrum that I've sort of found there is quite substantially off what we know from the numerics. And so I think it's a pretty difficult experiment because you should really probe locally the system. But nevertheless, qualitatively, its own suspicions. So that's if Ali has done, it would come here, probably he would show this slide. This is from his paper on SNAPS 2010, and this paper at least close to metal-insulator transition in the semiconductor system and spatially measuring just tunneling density of states in the system and observing functions, qualitatively similar to what I showed. So now it's a completely different type of experiment. It's ultrasound. Yeah, I told you that in principle, same physics. It's just in classical problems of wave in disordered media. And this is, for example, ultrasound spectrum in the system of random detect aluminum beads, small balls. And yeah, so you see this wave functions and you see the small fractal spectra, but once again, if you quantitatively look at them, they're differ quite substantially from what we know should be three-dimensional system from numerics. But quantitatively, it's a very nice experiment, and one more is a light. Localization of light and the rate of the needles, and again, it's a pattern of some mode, light, and say more about this experiment. Yeah, so now let me say some words about one very interesting, curious property of this multifractal spectra that we first found some years ago by just doing explicit calculation with sigma model, and you always can describe this critical point with sigma models, and even without explicitly calculating the spectrum, one can show that there is this symmetry that the exponent with index q is equal to the exponent with an exponent. So this means that this, and now q is any number, it should not be integer, it should not be positive, in fact it should not be even real, but it's real, but in principle it can also be counted. And this means, so if you take q like some positive number, I don't know, like 3, so this, and this one molecule will be -2. So the big positive moments probes probability to have a very big amplitude of the functions. So negative moments probability to have a very small functions. Yeah? So there is a relation in the distribution of eigenfunctions which connects the probability to have very big to very small. Yeah, that's not the obvious symmetry that you would expect. Nevertheless, there is an exact symmetry of this condition. Yeah, so you can also express it as a symmetry property of this f function. Yes.
Is this coming from the nonlinear sigma model, or is it much more general observation?
It's coming from the sigma model, and it's very general. The reason is the following. You can always construct a sigma model that will flow into a given critical point, into a given fixed point. Yeah? Even if the sigma model will be in strong coupling, and which means you cannot really do any explicit calculation of the sigma model, but it exists, eh? And it's the only thing that we need. And therefore, it's a property of the fixed point, but to derive it, we use the sigma. Yes, well.
Is this universality class independent?
I will show. It exists for other universality. So in this way, it's valid for 3 Wigner Dyson classes. I will say about this. For other classes, it also exists, but in a modified way. I will show. Yeah, so for example, here it's shown that the symmetry exists in numerics, and what is shown here are results for this power law random Bennett matrix model with large and also with small b. So small b is exactly the regime, or b of unity. This is a regime where we cannot do analytical calculations with a sigma model. Yeah? Nevertheless, we are sure that this is an exact statement, even because you can construct a sigma model. So this is a sigma model which floats in those fixed points, and that's sufficient. Yeah, and so yeah, it's clear that there are questions, and so one is, what is actually a reason? Is there any? I mean, we just got it from the calculation sigma model. Can one? Is there some symmetry reason for this certain symmetry of the problem that would be responsible for this? what are generalizations to other symmetry classes, as Leo asked. And more generally, so that's only a property of these moments of wave functions. However, and there are corresponding operators. One can ask about generality of this. If I look at more general, the whole system of operators that are described in some wave function observables, not only moments, there's a much broader class that I will show how to construct them and whether there are also corresponding symmetry properties. Yeah, and so there is a very sort of long paper just recently appeared by Ilya Gruzbeck, Martin Simbaum, and myself in TRB. That's what I will say now. You can find in great detail there. It's pretty mathematical, and I will just give you now ideas and flavor without details. Just presenting this paper will take the whole 4 lectures. So first of all, classification of scaling observables. Consider n points, R1, R2, Rn, and n wave function, set 1, say. So for each t smaller than n, define the following objects. So this d is just a slated determinant based on wave function psi1 to psi t in points R1 to Rp, and AP is just the model square of this slated determinant. Then, for any set of numbers q, in general they can be even complex numbers, define product of such determinants. So you have determinant A1 for one wave function, it's just wave function squared. A2, this is a Hartree-Fock type of the matrix element of the sort that would enter Hartree-Fock. So structure would enter typically in the Hartree-Fock matrix elements, and suppose A3 and suppose to any powers multiply them and average over this order. So it's a very complicated looking observable. So the statement is that these are pure scaling correlators of wave functions. So pure scaling means that on the RG it scales as just one exponent. To prove this, we go to sigma model. So we make this on the operators in the sigma model, and then show that the sigma model operators are just pure scaling operators. So what are corresponding sigma model operators? So these are composite operators, so there are some functions of Q, and they are constructed of the function Q in a way which is quite intuitively understandable if you look at the definition of this object in terms of wave function. So it's a product of this d1, d2, dn, so the power where dj are constructed as out of matrix Q, where so Q is this super symmetric matrix, and now it should be considered as a big matrix. Yeah, it should be of a large size, because that was the question before that one should enlarge matrices, and in this case one should, because it goes to more complicated observables. So dj is a principal minor, which is a block of this matrix Q, and not of Q, but of some combination of. So 1, 2, 2 are this retarded advanced subblocks and retarded advanced decompositions. BB is boson part. So anyway, so one can construct out of the matrix Q first this object, and then takes some minors of this to corresponding powers, multiply them, and this is an observable. This is a explicit composite operator that corresponds to the observable types of wave functions. Yeah. So to go from wave functions to here, one just does explicit computations. So we know how to make observables in terms of green function on the sigma model, you just go through it in complex description. Yeah? And it's relatively straightforward to express wave function correlation in terms of green functions, and then just use an arguments. Now,
what's the definition? So DJ is the principal line size JJ of the Q matrix, or?
of the Q matrix, yeah. Of the big, of the, well, of the Q matrix, but still one should do some massage with the Q matrix. One should take sort of block of this Q matrix. One should take boson block and in retarded advanced decomposition make some.
So it's not it's of this combination,
yeah, so this is more or less, this is some block. So the Q matrix is 2 by 2, it's 2 matrix if you consider block structure in boson fermion space, and also 2 by 2 matrix if you consider it in the retarded advanced space. Yeah. So, and you take certain block in boson, that's boson, and in retarded advanced decomposition you project on this. It still remains a matrix n times n, because you consider now big Q matrices, you need to enlarge matrices. And out of this matrix, you now take this.
But is this a supersymmetric matrix? Or?
Well, Q originally is supersymmetric, but now it's a boson block, so it's a normal, it's a commuting part.
Okay, and what is other components? I mean, there's a retarded advanced part, but you're saying you have n species somehow?
So this one means retarded, 2 means advanced, and 1 2 means so there is some combination of retarded and advanced, and that's natural combination, because when you calculate density of states, you have GR minus GA, and it's retarded minus advanced. So that's how this thing come about.
Oh, but it sounds like there's an additional space of Q. You know, Q. There are many flavors of bosons, or?
Yeah, there are many. That's what I was trying to say. Yeah. So you should start by. So in the simplest version, when we derived the supersymmetry, we started from a super vector which was of this type, and that was sufficient to represent the product of one retarded and one advanced. However, we now have many of them, and because of this, we should make many flavors of this.
So it's like replica flavors, right?
Yeah, but these are not replicas. These are replicas, but there is no replica limit. You just introduce as many as you need to. If you have a big correlation function, you have to reproduce or have many of sufficient
you
many.
Want to distinguish those different.
Yes. Okay, now to show that these are scaling operators, and also to find their properties. Well, now it's some math. There are 2 different ways to do it. In one very sort of nice way is based on the Iwasawa decomposition, and that's yes.
So I have a dumb follow-up to Leo's question, which is, let's say I only care about 2-point correlators in the nonlinear signal model. Could I just introduce a bunch of extra fields, and then somehow these guys act trivially except for the first 4?
Yeah, so of course you can
calculate high correlators.
Yeah, of course you can always introduce many of them, even if you do. So for lowest order, if you just calculate moments of wave function, then this is sufficient. Yeah, you don't need to. However, if you introduce more, it will not make any harm.
Is it? But I guess I'm asking is if I introduce more, do those somehow come into the action completely trivially? Because I'm just never.
No, you will have a theory of big Q matrices, and here you will have to take out of this Q matrix just some certain angle. So this operator will correspond to some angle of this Q matrix.
Okay, so if I introduce more flavors, even if I'm calculating low order correlators, those flavors nevertheless act kind of non-trivial. They all
no, they will be in the theory. So the theory will be a theory of now big matrices with flavors, and they will of course in the sort of action of the theory they will all mix, and it will be just a big matrix, and that's it.
I have 2 questions. One is, why can't I just introduce a field coupling to Q and take derivatives with respect to that.
One, introduce what?
External field coupling to Q, like a magnetic field,
Okay.
and just take functional derivatives and do the calculation, right? Where you need n copies.
Why? So you ask why do I need to sort of to multiply this? Why do I need to introduce flavors? Is it?
Yes.
That's because. So once again, so if you calculate just moment of say one wave function or moment of density of states, you don't have to do it. It's sufficient to introduce one, and you can generate all moments, for example, by introducing a source if you want, or just
Right.
by starting from the product of, from the nth moment of the green function, you can make it on the sigma model in this way. However, now, when you have objects like this, when you have antisymmetrized product of several wave function different points, then it turns out that if you will not be able to obtain things like this by having only a small vector. It's because if you will have this, you will always get something which will be sort of symmetrized. If you will do what you propose, you will never get this antisymmetrized construction. So
Is it because
to obtain it, you need necessarily to increase the symmetric sense.
Is it because the different wave functions are obtained at different realizations of this order? Or are these wave functions?
No. All wave functions are in the same realizations of disorder, yeah. But there are just different wave functions, and so you need to generate this. That's a little technical. Well, it's mathematically it's also related to the fact that you will need higher representations or young tableaus, and to get this you need a bigger group. Yeah.
That's the second question.
Yeah.
So I could take the sigma model and enlarge it, use many flavors, but simple things like the RG flow, etc. They shouldn't depend on it.
Yeah.
And that's true.
Yeah. So the sigma model, the RG flow for say conductance will be the same. However, large sigma model will allow you to define composite operators that do not exist in the sigma. Okay, good. Yeah, so the way to show that the scaling operator studies the properties is based on, actually, two ways. One is based on Iwasawa decomposition, and the Iwasawa, and yeah, there is another one of constructing this function as a highest weight vector, so value highest weight vector. So it's all now about classifying spherical functions on this complicated manifolds. Yeah, so we know the spherical functional sphere. They classify it by so angular momentum and the projection of the angular momentum, J, M. Yeah. So there is basically we need the corresponding analysis here. It's just much technical and more involved. So highest weight vectors are those that have a projection of the angular momentum M equal to G. That's yeah, so let me just quickly say what is Iwasawa decomposition. It's so you generally have sigma model space G over K, where K is a maximal compact subgroup. So I showed the examples of these symmetric spaces, and so one, the simplest one is shown here for this unitary class, like for example for one Hall transition. And so Iwasawa decomposition is decomposes the group G into the product of K. This is what we want to divide out. A, which is a maximal abelian, so group in G over K, and the rest is important, which is represented by triangular matrices as one on the diagonal. And it's in fact generalization of what is known as Graf-Schmidt decomposition by representation of the matrix as triangular times unitary. So this M corresponds to triangular, K to unitary A's, which is there. the beauty of doing this is the following, that once, so basically it means you go to new coordinates on your tube. Okay, and these coordinates correspond to this, coordinates corresponding to this abelian group A, and the rest is important. And now we can look at wave functions, spherical wave functions. In each representation, there are many spherical wave functions, spherical functions, as we know, and you can choose in each representation one that you prefer, which is invariant with respect to. And here you can choose one that is invariant with respect to n, which depends only on coordinates on this A. And it turns out that in this coordinate, these spherical functions look simply as planets. Yeah, that's a very general statement, and so that's a way to construct. So you go to this coordinate system, and then you know that spherical functions just simple explanations. Yes.
So I have a question about more simply saying this structure. Can you draw an analogy with the O2 by O1 group and show how the coordinates work on that? So O3 by O1.
So let's, maybe I'm afraid that if
Okay.
start doing this explicitly, let's kind so I would prefer to proceed, so maybe let's leave it with it.
Sorry, can you summarize maybe what's the goal right now?
Yeah, so that's what I want to show. The next one, I think it will be. So basically, that's a way. So first of all, that's a way to construct the spherical functions, which are eigenfunctions of the Laplace operator and also eigenfunctions of the normalization group operator, any invariant operator. And in fact, one can show that if I these wave functions are exactly those that I showed you before. So these functions Q are identically the spherical functions that you get within the sinusoidal position. So in this way, you show that there's or you construct the spherical function, but it's not only what you do, you can also show the symmetry. And that's, so once again, I can only declare this this moment because it requires a math. So all this has been known in non-supersymmetric version. Yeah? And so the corresponding reading for this are books by Helgason, which contain physics of beautiful books on the algebras and symmetric spaces. And, so, what is interesting, it's one to recommend. And so basically, what we do is a supersymmetric generalization of this. And it turns out that there are symmetries which are known as a wide group, and the symmetries tell you that eigenvalues of any G-invariant operator, so the spherical functions will be eigenfunctions of any operators that is invariant on the group G, like Laplace operator or like RG operator. Normalization group is also the invariant operator. And then there are symmetries which correspond to changing this. So this X, J are coordinates on this group A, and Q's are coefficients which play a role as essentially angular momentum. So you can think of these Q's as and these are spherical functions, and they are parameters. So that label it as corresponding angular momentum. It's just a Riemann of this momentum here on these manifolds. And there are symmetries that tells you that you can make a reflection of this momentum with some shift, and the eigenvalue will not change. So there is a reminiscence of this if you just look at eigenvalues as a just conventional Laplace operator on a sphere. And the eigenvalue is j times j plus 1. And if you look at this object, it's symmetric with respect to j going in minus 1 minus 2. Of course, you cannot do this on a sphere, just because sphere is compact and there is no. So j is positive integer. However, if you do to go from sphere to hyperboloid, then the corresponding momentum can be already in. And there is no compactness on hyperboloids, there can be any value of the so say angular momentum. There is no reason for it being integer or effectively zero. And so there are symmetries of the corresponding value of the Laplace operator on the hyperboloid of this sort. And now these are symmetries which are simply generalized to the symmetric spaces. And remarkably, it turns out that the symmetries lead to symmetries of the, for example, this multifractal exponents, because they apply not only to eigenvalues of the Laplace operator, but to the symmetries of eigenvalues of any invariant operator. And that's one of the manifestations of the symmetry is the symmetry of the multifractal spectra. However, we can also, there are many more of this because there is now the whole construction that there are much more operators, and out of any operator, yeah, so this multifractal corresponds to, if you just have one q, so just one moment, you go to the operator, which is 1 minus q, and then you have the same eigenvalues. But if you have the operator which has two q's, q1, q2, which means that you have the product of, you take first two here, a1 to some power and a2 to some power. So big function and 2 by 2 slated determinant to some powers, multiply them. So for any pair q1, q2, you construct 8 more that should have the same eigenvalue. So, and as an example, take this object, just take this slated determinant. Now we are back to simple physical objects, and take the slated determinant, raise it to the power q, and this will correspond to eigenvalue delta q, delta qq. And according to the symmetry, the eigenvalue delta qq should be the same as 2 minus q to minus q. So the multifractal spectrum of this slated determinant is symmetric when we go from q to 2 minus q. And now I show numerics by Schumann here. There's nothing. So this is a numeric by Schumann. Then he was still in Karlsruhe, and so the Ferdinand errors, they just deep modeling of moments of this object, and one sees very nicely that the symmetry of this with respect to the q going to 2 minus q, and this is a symmetry. Yeah, this is a modeling as a quantum Hall critical point, and so this is a symmetry that doesn't follow from any S symmetry q minus q of fractal spectrum of wave function. This also doesn't show from any simple intuitive considerations, any simple explanation for it, and we don't know how to guess it without discovery. So this shows how, I think it's a very beautiful demonstration how this structure, the sigma mode manifolds implies some observable properties of the critical points. I don't know whether there are any other situations except for
sorry.
others. Yeah.
So why do you have error bar on one side but not on the other hand?
That's questions to Schumann, not to me. Because he did. Okay, of course I can answer without him. Yeah, that's easy. So these are moments. So when you, these are larger moments, and of course, so this, for example, moment number 0. Yeah. So of course, when you calculate moment number 0, there is no error bars because you average units. Yeah? So when your moments are larger, then error bars are larger, in particular because when you study high moments, you draw probabilities of the wave function to be, of this object to be sufficiently big. And that's, so you start to problem tails of the distribution function. Because when you probe tails of the distribution function, the uncertainty becomes bigger. That's the usual story. High moments. But all details, yeah, since sure, should be somewhere around asking about this. I don't know why they never published this. Yeah. So now there was a question about classes, symmetry classes, generalization to symmetry classes. So I understand that Alex Altman told you about symmetry classes, so I don't need to go into much detail. So let me just show 2 slides on. So in total, there are, as it's understood now, 10 symmetry classes, which so 3 of them are these normal Wigner-Dyson classes that you enter if that you encounter sort of in usual situations, and which of them you get depends on whether you have, in physical terms, whether you have time-reversal symmetry or spin rotation symmetry. And there are 2 more groups of classes that have some particle hole symmetry. And these are chiral classes where Hamiltonians have this structure, or the Leloup-de classes where Hamiltonians have this structure, and this is characteristic for disordered superconductors. So, of course, in this for symmetry classes, you get this symmetry only at one certain point in the spectrum, namely at 0 energy. So they are, in this sense, much less generic. So you have this Hamiltonian, but you go away from 0 energy. So the energy breaks the symmetries, then you go sort of sufficiently big that you are simply big in this class. However, if you are, for example, in the disordered superconductor near 0 energy, or in graphene, as I will discuss, certain types of disorder near 0 energy, or so if you have particle hole symmetry, or something that plays a role with particle hole symmetry and want to be near 0 energy, then additional symmetries will get to this symmetry classes. So I understand that Alex explained that there is a relation between the symmetry classes and the symmetric spaces, between families of symmetric spaces, both on the level of Hamiltonian and on the level of the sigma model. So for example, if you take this class A, which is a class that there's no symmetries at all, this is a discussion in the context of quantum Hall effect, that you just have sort of all symmetries are wrong. No symmetries at all from the point of view of the Hamiltonian. The corresponding symmetric space is just the group UN. It's just because A is simply, it's Hamiltonian, it's just Hermitian matrix, and Hermitian matrices form, if you multiply by I, you get anti-Hermitian matrices, and they form Lie algebra for UN. That's correspondence. And so for other ensembles, the corresponding spaces of matrices will form a tangent space to the symmetric space shown here. So there are 10 families which are obtained from groups unitary orthogonal symplectic by factoring. So 3 of them are just this group, unitary symplectic orthogonal, and all others are obtained by factoring maximum complex the sigma models corresponding to each of this class again leave only on the symmetric spaces. Yeah, now in the supersymmetric setting, the sigma model has a compact and non-compact part. As I explained, it's a sphere times hyperboloid, traced by something Riemannian, and therefore the sigma model one writes here two symbols. Yeah. So this symmetric spaces all. So this is all classifications, cartons. So this symmetric spaces with some names, which are letters A, B, C, D. There's numbers 1 to 3 that are related to classification of root systems. And so the sigma model will have a compact and non-compact base. So the base of the manifold will be a product of something compact and something non-compact, and each of them will be corresponding to one of these. For example, for this UN, for the class A, where the Hamiltonian corresponds to the just UN, the sigma model symmetric space is, as I showed you, U divided by U cross U, and this is what is called A3. And this is A3 for compact, A3 for non-compact, and so forth. Yeah. So you see these symbols here and here are the same, but they are just reshuffled. Yeah. Good. So we will discuss in the rest of the lecture some properties of systems in different symmetry classes and some criticality, what is the influence of this on critical points. So let me, before we go to this, just answer the question Leo asked about the symmetries in different symmetry classes. Yeah, so in general, for all symmetry classes, we have symmetry properties. So the points with respect we have to reflect a different, and actually for 5 symmetry classes it works in a most simple way, and for 2 other it works excluding some domain walls, because it turns out the sigma model manifold here lives on 2 disconnected parts. And by the way, in this way we can improve that these domain walls in the sigma model language are simply responsible for localization. And for 3 classes, which are parallel classes, it turns out that proof doesn't work, because there is additional Abelian U1 degree of freedom that spoils proof. So it's not, in the simplest form, it's not. Yeah.
Could you talk about how to obtain the symmetry classification as well from the point of view of the sigma model? Because Alwyn talked about how to obtain it from the Hamiltonian, and so it would be great to see the derivation from the point of view of the sigma model as well.
Well, so basically you can, so starting from any Hamiltonian, you can map it on a sigma model. Yeah? And so when you do the mapping, so for example, as I say, yeah, when you start from just this class A, where the Hamiltonian, there's no symmetries at all. Yeah? And as we went through this mapping, and it turns out that you map on the matrices, the Q matrices that are, you have this retarded and advancing sector, you have this matrix lambda, and you should, as a result, the symmetry is U2n over UN cross UN, which is what we call H3 symmetry. So basically you can repeat this derivation for all classes, and then you know for each class which sigma model you get. Yeah, I will not. So of course you get exactly this. Here you have 10 classes, and here you get sigma models. They live on the same 10 classes, but they are just in a sort of going here in different order. Well, I would not immediately, simple argument how to say without calculation which one will correspond to which one. But are not existing. So I think the question is essentially, you can write a sigma model on all these manifolds. Yeah, that's clear. If you don't care what it describes, you can write it. And basically, these sigma models have been written much earlier than all this topology. So there are old papers where people studied all these sigma models and calculated the beta functions up to 4-loop order before this discussion of symmetry classes of disordered system appeared. So there are papers by Wegner, by Shikami, I think, first in beginning of 80s, I think, where all sigma models have been studied periodically. And that's because this has been known in mathematics that these are 10 families of symmetric spaces, and the moment you write one sigma model, like Polyakov renormalized the spherical sigma was a vector sigma model, then a few years after this, people renormalized all sigma models and all symmetric spaces. And more recently, it has been understood what is a connection between sigma models and yes.
Why you just look at, I'm not sure, it's accidental or not. So the sigma model symmetry happened, for example, in the Wigner Dyson class, happened to be the ones of the symmetry of Hamiltonian in the Cairo class, and vice versa.
Yes, that's correct. Yeah, there are such.
There are some reason for this?
Oh, yeah. Well, no, I don't have. Well, I know, of course, why it happens in the calculation, but I don't think I can, in simple words, why it should be so. No. So, so maybe we go to another slide and then it will be. It will not answer, but maybe it will be some more information. So that's okay. So this I think I said. So the symmetries. So you see now there is a very rich sort of zoo of these theories on corresponding to fixed points. Just because now we have, in addition to dimensionality, of course, I explained to you that physics depends on dimensionality. That's clear, but it also depends on the symmetry. And already for Wigner Dyson classes, as we discussed yesterday, what happens depends on symmetries. So the beta function in 2 dimensions, and now we will largely speak about 2 dimensions because it's one of it's probably the most interesting dimensionality is with a very sort of rich type of behaviors that we find. So in 2 dimensions, the beta function for orthogonal unity in symplectic classes as sketched here, and so we have 3D. So for orthogonal unitary, it's always negative, so you get localization. However, the localization like for unitary is parametrically larger than for orthogonal, because the beta function here goes like 1 over g and 1 over g squared correspondingly. And for symplectic class, we have even a transition to dimensions. So that's already seen in Wigner Dyson classes, that symmetry is important. For when you include all 10 classes, of course, you get still much richer types. Much sort of richer zoo of these types of behavior, but it's not the whole story because in addition to symmetry, there may be a non-trivial topology of these field theories, and it may change the behavior, and in particular may protect the system from localization. So, famous example of this is a quantum Hall effect, which again been discussed here, I guess, by John Choka, and probably can also show this flow diagram.
Sorry, can you just go back one slide?
One slide, okay, this one.
Yeah, so this says unitary in 2D is always localized.
Yeah, so this says unitary is always localized, and now we go, that's exactly what I was going to say, yeah. So this says unitary in 2D is always localized. Now, quantum Hall effect, yeah, so this I don't need to explain, I guess, after John Choka's lectures are shown here. And we see that's the same unitary class, but it's not localized. So first of all, we see these peaks, so there are points where you have so this rate is a longitudinal resistivity, so the points where it's non-zero, and also on these plateaus, even though here the longitudinal resistivity is 0, the whole resistivity is not 0. So it's not a normal insulator. Normal insulator would be everything is So something is different from what we would mainly expect in the unitary class, and the corresponding theory has been understood by Pruskin, that the corresponding theory has an additional term, which is shown here. So this is a usual term, gradient Q squared, and the prefactor here is just conductivity sigma xx. But in magnetic field, there is also a conductivity sigma xy. It turns out that in 2 dimensions, in the presence of broken time reversal symmetry, you are allowed to write another term, which is also the second derivative term, it's Q, which is shown here, and as was shown by Pruskin, that's exactly the term that comes out when you do the derivation of the sigma model in the presence of magnetic field. So it's now not sort of single parameter scaling, but 2 parameter scaling, and the remarkable property of this term is that this is a topological term. So if you would do perturbative calculation, renormalization, it will never show up in any order of calculation, so perturbatively it sort of doesn't exist. And this is because it's topological, so what this term does, it counts winding number of your 2-dimensional plane, that think about as 2-dimensional sphere, if you compactify it, that is mapped onto the corresponding sigma model manifold, which is this U, and it contains a complex sector, which is U2 over U1 cross U1, and U2 over U1 cross U1 is just a sphere, just a normal 2-dimensional sphere, and so it's a mapping of sphere on a sphere, and can be any integer number of windings. And this term exactly counts how many windings we have. So this is what is called the theta term in the field theoretical language, and the role of the angle theta is played by the whole conductivity. So the corresponding flow diagram, our chief flow diagram is shown here, and this was understood by Litsky and Pruskin. Now, so what is shown here is this is sigma xx, this is sigma xy. At 0, sigma xy, we are on this line, and there is no arrow, but the arrow on this line is downwards, as all arrows here. So you just flow to 0, to localization. Without magnetic field, you just flow to localization. However, when you have a finite magnetic field, you can flow, so from most of the points you flow down to sigma xx equal to 0. However, sigma xy can be 1, or 2, or 3, and these are exactly these plateaus. So this corresponds to different topological states of this monopole effect. It's the first example of topological insulator, and this is these are different topologically distinct states. And of course, between them, there should be a point where the flow is split, and so there should be necessarily some fixed point on this line, and this is a minimal guess, let's say. Of course, nobody can really sort of calculate what happens here, so this is sort of reconstruction of this phase diagram out of the information that we have, and this is a minimal reconstruction, and all what we know agrees with this, yes.
But is it demonstrated that this topological term does this, or it's just believed that it can, or
okay.
How much?
So what is? Yeah, it's of course it's a combination of calculations and sort of educated guesses, and that's so the calculation. The only thing you can do is to calculate here where sigma xx is large. Where sigma xx is large, the topological term doesn't show up perturbatively. However, if you include non-perturbative contributions due to instantones, it does appear, and if the because they're exponentially small in this regime, it still gives a contribution that will show that there will be a flow which qualitatively has the structure. So it means that here it will deviate this direction, here it will deviate this direction, and there will be correction to sigma xx such that we delocalizing corrections, so to say, to sigma xx on this line.
You
However, in the regime where you can calculate, it's exponentially small thing, and of course, in order, this is once again, this is already an educated guess, yeah, that's, you just should extrapolate this to the range where it's, strictly speaking, your calculation is not applicable, and guess what may happen there. But in addition to this guess, we have, of course, experiment, and we have numerics, and combination of all this says that this is a correct flow diagram. However, of course, I should warn here that one should not take this too literally, in a sense that, of course, the true fixed point of the theory is, of course, not close to sigma. Yeah? So the true fixed point of the theory is nobody knows what. It's some complicated, strong coupling theory, so people tried to guess it should have conformal symmetry because it's a critical point. There have been attempts to guess this theory, and the sort of guesses that this is some very sort of complicated version of Westermüller-Witten theories on this. However, they have not been particularly convincing, first of all, and I think they also disagree with what we know about multifractal spectra, and there is no. So at the moment, I would say, since we don't know what these fixed points are, and it well may be that there's such complicated theories that we have no sort of chance really to describe them. Yeah? So what we do know that that this sigma model, when sigma xy, when theta is equal to pi, when we are exactly on this line, will flow into this fixed point, and that we know for sure. So one should understand this flow diagram from this theory in this restricted sense.
Is there a way to make contact between this topological term and the Chern-Simons term of the effective field theory? Or are they unrelated?
Well, as you know, there are many terms that all have sort of topological nature. So this term, contrary to Chern-Simons, that's topology. This term doesn't exist on the perturbative level at all. That's whereas Chern-Simons will also exist perturbatively. So it's so maybe we'll classify. We'll now go to other types of topological terms. We'll also, so just wait a moment. Yeah.
So there are those unstable, or rather stable along one direction.
Yeah. So this fixed point, these fixed points are stable on this axis,
right,
and unstable against this.
So they have some sigma xx value.
Some sigma.
Some value of the longitudinal.
Yes, some value of sigma xx of what unit is some number.
So is that experimentally substantiated? Like
what is the number?
Yeah, the number is universal. Is that substantiated?
Yeah, I think there are. It's at least reasonably. Agrees reasonably because experiment. However, one should be careful here when one compares to experiment. So now we are discussing non-interacting theory. So experiment normally one studies theory of school interaction, which belongs, as we discussed tomorrow, to different universality classes. However, qualitatively the flow diagram turns out to be the same. So interaction changes the fixed point, and so the number may change a little, or maybe not a little, may change by some number for the unit. Yeah, but qualitatively the structure is the same. So we also with interaction we expect that there is a similar sort of flow diagram. However, of course, with interaction there is a more complicated flow with interaction, but in the end there are also these fixed points, and with presumably some universal number. Yeah. So without interaction, we have numerical calculations that this number is something of the order of 0.5 units of the spherical age. However, again, one should be careful how what one calls in the calculation, and because so if one defines reasonably the conductivity, one should still define what's conductivity, and then it's more or less 0.5, 0.6 squared to h without interactions and numerics. So interaction value are actually not so much different. I think it's reasonably okay. Yeah.
This number, when you go, for example, to calculate higher order correlation functions, or when you introduce these extra copies, does this same integer classify the mappings from the original space to the target space of the nonlinear sigma model, or is there a chance that?
So you ask whether if you go to this sort of increase the number of flavors and go into sigma models with, yeah, if they will have same. So basically, what determines the existence of this topological term is a homology group. Yeah. So it should be. So in this case, a homology group pi2, which means that we're mapping from the sphere onto this corresponding manifold. The sigma model is Z. And this will remain true also for higher if you multiply number of records. So it's still there. Good.
So,
Yeah.
so where do you get this term sometimes and sometimes we don't? It vanishes when it's not in other cases, or?
Which term? Oh, this topological term.
Yeah.
So the topological term has sigma xy here, and this is always correct. So if there is no magnetic field, just sigma xy is 0, and so this term doesn't exist. And at the moment you have a magnetic field, you have this term. So that's.
But you could you have the matrix is Q in the unitary class, but sigma xy is 0? Well, spin all.
No, sigma xy is not property. I'm not sure what you call
well, I mean, so there's two ways you. I mean, you could if you're allowed to have a topological term, it doesn't mean that the coefficient in front is there are many separate.
if you allow what?
You know, if your theory allows a topological term.
Yes, the theory allows a topological term, but the coefficient, the theory doesn't tell you what is a coefficient. It can be any number. So because it's a Z, it's a group Z. So we now discuss soon, hopefully today still, a situation with a topological term with a group Z2. Then the coefficient here can be only 0 or pi. When the group is Z, the coefficient here can be any number.
But including 0.
Including 0.
So you
And
cannot
it's just sigma xy. So take your theory in your magnetic field with your disorder and with your, and just calculate on a level just quasi-classically sigma, what is the value of your, just do that self-consistent Born approximation and calculate what is the whole conductivity. This will be the value of the Bayer coupling here. Then calculate sigma xx, sigma xy, then you know where you start on this here, and then you flow. That's it. If you don't have a magnetic field, then of course, in the same imagine you have only a random magnetic field, which fluctuates symmetrically around 0. Then it breaks time reversal symmetry. However, sigma xy will be 0. Then you will be on this line. Yeah? So of course, you can create an ensemble that will have broken time reversal symmetry. However, sigma xy equal to 0.
Right.
It's just random magnetic field fluctuating symmetrically with respect to 0.
Then it's known it will be insulated.
Then you will be here, and then you will flow. In the moment you introduce sort of average magnetic field as well, you shift somewhere, and then you can flow.
Or you can have like a quantum spin model.
Yeah, and I have some plots, I still hope to show them. Yeah. Let me give you some examples of importance of the symmetries and topologies in models of graphene with some disorder. So I need to explain because, well, it will be models of 2D Dirac fermions with disorder, so it may be graphene or maybe topological installation. But I will maybe discuss in the context of graphene, yeah. Yeah. Okay, so that I want to just to motivate why we look at it in principle. We can look at just on the theoretical level. However, there is also a sort of experimental indication that it's maybe interesting to look at critical points of graphene with certain types of disorder. And the indication is the following. So, well, I think everybody knows this plot of graphene conductivity as a function of the gate voltage, and so this is a Dirac point. And now, of course, specific data depends on the experiment, but in one of very nice experiments some years ago, Philip Kim looked at the conductivity at the Dirac point down to very low temperatures. Yeah? And so this red points correspond to conductivity here, and so what was remarkable, I mean, that's really steep, but that doesn't matter. But so the remarkable property was that it essentially stayed constant here down to temperatures like 30 millikelvin, and that's what, at least in some experiments, is observed. It means that there is no indication of localization. Yeah? Now, this 30 milliK is pretty low temperature, so if you estimate what is the mean free path here, it will correspond to the temperature like 30 Kelvin, so it's 3 orders of magnitude below. And normally you would expect, yeah, and the conductivity here is of order of E squared over H. And normally when you have the conductivity of order of E squared over H and you go to very low temperature, you expect to see localization as we discuss it. And yeah, that's, I think I already showed you in the wires how. And that's similar in two-dimensional systems. Usually, if you're in a semiconductor system, you create conductivity. It's a dirty semiconductor system with conductivity squared of H. You go to low temperature, you see it localizes. It goes to variable range hopping, and that's it. And this doesn't seem to show it, and so one can ask a question: can it be, or for what types of disorder may it happen that the graphene at the Dirac point will not localize? Yeah. Okay. So let's discuss this questions. Okay. So I don't need to explain what's here. So the Hamiltonian, the low energy part of the Hamiltonian of graphene is just 2 Dirac Hamiltonians corresponding to 2 points, 2 values k and k prime. And yeah. So the Hamiltonian. Yeah. So you can introduce. So additional, so 2 sets of polar matrices, so sigma correspond to sublattices, this is 2 by 2 Dirac Hamiltonian, and tau correspond to 2 values, and so that the whole Hamiltonian can be written like this, and V is some randomness, and in general, I can write a randomness which has any structure in sublattices and in value space, and of course to analyze what we will get, we need to analyze symmetries. And the clean graphene has a lot of symmetries, and these symmetries are as time reversal, true time reversal. There is a chiral symmetry, there's a particle hole symmetry when we see the Dirac point, and there is a isospin symmetries between 2 values. Yeah, which is very much symmetric, and so multiplying this isospin symmetry components of this isospin with time and chirality, you get 3 more time reversal symmetries and 3 more chiral symmetries. I mean, 3 more symmetries of the type of time reversal. So now you can look which of these symmetries are respected by disorder, and depending on this classifiable symmetry class. So now what do we expect with conductivity at the Dirac point? So of course, yeah, again, everybody has seen of calculations. So if you just do naively self-consistent Born approximation calculation, you get this number 4 over pi squared of H, where 4 is due to the degeneracy, 2 spins, 2 valleys. But of course, this calculation for generic disorder, it doesn't make much sense because you will have localization that will drive, let's say, conductivity of order of unity in units of the squared of H, and generic disorder will immediately drive you to localization once the temperature is below the mean.
Who's special to Dirac? The vanishing density thing.
Yeah, so this is calculated at the direct point. Yeah, that's why you get a number which is of order of square. That's one of the tau cancelled here. So there is whatever the self-consistent, well, the quasi-classical conductivity is of order of unity independently of the strength of the disorder. So you start from, because there's a cancellation, you have vanishing density of states, and density of states is produced by the same disorder, and so they cancel. So the question, can one still have conductivity which is not localized, which remains something like this, maybe with some different number, which means prevent localization. Yeah? And it turns out that this may happen for special types of disorder. And in particular, it happens if disorder preserves chiral symmetries, or one of chiral symmetries, or is of long-range character, and which means does not mix two layers. So for these two classes of situations, we know that there will be no localization, and I comment on this. Yeah. So this is more or less a couple of different types disorder respecting different subsets of the symmetries, and there's a list of what classes you get and what will be the corresponding values of conductivity. So you see, depending on what is your disorder, you can get a whole zoo. I think there are 6 out of 10 symmetry classes that arise here. And it's not only different symmetry classes, but there are also different, in some cases, different topological terms of topological origin. So there are 3 groups here. So one is what we call this CZ chirality, and this is a situation. So the simplest case of this, imagine you just have vacancies in graphene. Imagine you take randomly some sites out of graphene. Then this preserves the chiral symmetry of the Hamiltonian, and at the Dirac point, the particle hole symmetry is preserved. Yeah? It's I will show some more slides on this. So if you introduce on a site some potential, finite strength, yeah, then it of course breaks the particle hole symmetry. But if you consider the limit of this potential going to infinity, it means you simply eliminate the site. Then the symmetry is restored. Because it doesn't matter whether it goes to plus infinity or minus infinity, you simply decouple the sign.
What do you do with A and B sublattice? You keep the chiral symmetry?
It doesn't matter. So chiral symmetry means that you can only go from A to B and never go from A to A.
Right.
It means that your Hamiltonian is block off diagonal.
Right.
So so it doesn't matter whether you take a vacancy from A or from B. Chiral symmetry. What's this?
No, but what I mean is you have the same distribution of vacancies on A and
No, it doesn't matter what's distribution. So if you just have vacancies, you preserve chiral symmetry. By the way, it's interesting question what happens when they are not equally distributed between A and
right,
B.
that's what I mean.
But it's an additional,
Okay.
yeah, it's an additional interesting question. But chiral symmetry will be independent of this. But this will correspond to the case of some extra zero modes. Yeah, but that's yeah. But let's first. So there are classes where you have this chiral symmetry, and now for chiral symmetry, it turns out that there is no localization to any order of perturbation theory. Yeah, I don't think I want to go into details just now, but it turns out that localization, there is an exact statement that to any mode of perturbation theory, the localization is absent in this chiral classes. Yeah, that's therefore you get a conductivity which is just number. So more or less, your semi-classical conductivity remains true quantum conductivity. Then there are 3 other types of classes where you have another chiral symmetry, and this is correspond if you add to the Dirac Hamiltonian some random gauge fields, which may be non-abelian from the point of view of 2 values. Yeah? So this Dirac Hamiltonian with random gauge field characterized by theories different symmetry classes, but all they will have Besson-Wiener-Witten term. I think Alex, I heard that Alexander has mentioned this, yeah, that then when you go from Dirac fermions to the field theory, you get this Berzolino terms. So Berzolino-Witten terms are also terms of some topological origin, but they are sort of distinct. I mean, in fact, they are similar to these topological terms, but in a dimension shifted by one. And this is a type of terms that prevents the theory from localization, very generic. Okay, maybe in the next lecture we'll see more words about this. So when one discusses the classification of topological insulators, that's just so we know that there are the surface states which are protected from localization, and this is one of the mechanisms that protects the state from localization is the emergence of this miniature. And finally, there is a third group which corresponds to decoupled values. So when there is not, when the potential is long, disorder is long range such that you neglect any scattering between two values. And then there is a very general statement: if the electron cannot go from one value to the other, there is no localization. And on a level of the sigma model, it's realized by fcp1 topological terms. Yes?
Does that correspond to the breaking, effect of a breaking time reversal?
Which one?
When you can't go from, because then you're stuck near one valley, which is...
Yeah, and I think I understand what you ask. So when you decouple two values, then the physical time reversal doesn't play any role. So the physical time reversal made one value into the other.
Right.
Therefore, if the values are decoupled, you don't care about symmetries, because now you should consider two separate Hamiltonians for one and that. However, there are additional time reversals, as I mentioned, additional symmetries of this sort that may be there or not. And so when you have Hamiltonian in one value, you may have still Hamiltonian of different types of disorder. So imagine you have 2 by 2. One value is just very simple. It's 2 by 2 Dirac Hamiltonian, right? And now you may add to it. So basically, it's 2 by 2. So there are 4 Pauli matrices, and so you may add 4 types of disorder, which will be random potential, random vector potential, and random mass. And now, depending on what you do, you keep. So if it's only random potential, then you preserve this sort of effective time reversal. If there are other types of disorder, you break this effective time reversal. Yes.
So in all of these, the conductivity still ends up as 4e squared over pi h with maybe a log correction.
Yes.
The experimental value is 4e squared over h.
Yeah. Okay. No, I don't pretend that I know how to explain the experiment. What I say that at least we know examples, or when there is no localization and we get either number or some logarithmic anti-localizing flow. Yeah. I don't pretend that I can explain experimental number. Also, do not forget, as I mentioned, that in experiments there is interaction, and all these fixed point values are somewhat renormalized by. So I think the nicest, the one which is I think closer to that, is the one that corresponds to this one, and that's what I just wanted to mention, but I probably should get away in the next lecture. So if you have decoupled values, I think it's on the next slide now. Yeah, so it's the last slide that I showed today. So let's consider this just this situation. That's 2 decoupled values, and so we can consider them separately. And then, if there is a most generic type of disorder, then this effective time reversal will be broken, so everything will be broken. And it turns out that then we get plus A, which is a unitary plus, the same. And in addition, you get a topological term. This is the typical pi topological term. And so here it comes not from there is no magnetic field. However, you do get a topological term, and it comes from the Dirac fermion nature. So when you map this problem, Dirac fermions, with randomness onto the sigma model. So the fact that you deal with Dirac fermions generate you a topological term. So there are different yeah, you can just derive sigma model straightforward ways if you're sort of careful enough. And this, of course, related to chiral anomaly, and this is related. You can go to it by a Zumina term by just first considering clean Dirac fermions, getting the non-abelian Bosonization Zumina, and then introducing disorder in this Zumina will be reduced to this topological term, or you can straightforward derive sigma model. Whatever you will get this topological term exactly with the coefficient equal to pi. And it means that your system sits on this exactly at this point. Yeah? So the Dirac fermions with decoupled values and otherwise generic disorder turn out to be at the monopole critical point. And so the conductivity value will be the conductivity at this point, which is some number, but it's slightly, yeah, so it's somewhat less than what we need to explain this for, because this monopole, as I say, it's something like 0.6, 0.5, so it's more times 4, it would be still less. But however, on a qualitative level, it's similar. What is explained in experiment, I don't know. So in experiment, I don't know how to explain this discrepancy in number. And okay, so say last thing. So if you consider not generic disorder, still decoupled values, but preserved time reversal symmetry, which means that you just consider the random potential. Yeah. So for example, the generic disorder may come from ripples. Yeah. So ripples plays a role. Produce, in addition to random potential, also random vector potential, effective random vector potential. So they will validate this effective time reversal. So if it's just random potentials, the time reversal will be preserved. We will be in class A2, which is a symplectic class, which is related to the fact that we have this pseudo spin related to the sublattices, which is strongly broken, so it's a situation with one symplectic class. And in addition, the derivations, so when we derive the sigma model, turns out that we obtain again the topological term. And this topological term is different because for this symplectic class, the corresponding pi2 homotopy group is not Z, it's Z2. So this topological term may have only the value, the coefficient 0 pi, and here run it, and it is equal to pi. And that's, again, what protects this from localization. So at the moment you decouple these values, they don't localize, and that's exactly the state that you also find on the surface of a three-dimensional topological insulator. So this graphene with the potential disorder is essentially the same. Decoupled value graphene with potential disorder is the same state as on the surface of a 3D topological insulator. Yeah.
So there are these old results from Ludwig and Shankar and co-workers for single Dirac fermions for various types of disorder, and random scalar potential is marginally relevant and turns it into a diffusive metal.
Mm-hmm.
So why do we even need the topological term for the random potential to understand lack of localization?
Because so you see the series in sort of strong coupling from the, so the conductivity is a lot of units, yeah? So the quasi-classical conductivity is here 1 over pi, yeah? You could say, okay, it's a metal, it's a symplectic class, the value is 1 over pi, is below the transition point, so why wouldn't it localize after this, yeah? So this Dirac fermion theory only tells you, I mean, you can go up to the diffusion starts, but then you should see what happens. And in principle, you could expect that maybe it will localize there. Now, the fact that you have a topological term tells you that you can forget about this, you cannot localize. So yeah, I think we should, so maybe I take some question and short question, and then we should stop. Yeah.
So this RG flow in the presence of the topological term, is that analytically derived or is it guessed?
Yeah, it's the same story as the responsible effect. Yeah,
Okay.
Yeah, that's correct. So this is RG flow for the monopole effect. That's essentially the same. That's a sort of beta function which corresponds to the flow on this line. So this line here corresponds to the line theta equal pi. It's just this line, yeah. Just this. Oh, sorry, this line theta equal pi. Yeah. So this point is and it's one should not consider it sort of. So basically, one can calculate it here, and there are sort of qualitative arguments saying that there should be no localization, and so basically this is sort of drawn by hand, or we can do numerics and see what exactly happens. But of course, there is no analytic calculation in strong coupling regime. Yeah, that's so. What we do, we combine what we can calculate and the big coupling plus qualitative statements about the absence of localization, and then using the Occam razor by sort of minimally produces a minimal flow, and it seems to be the consistent with all what we see. Yeah, I think. Okay, so let's try that short one.
Yeah, so just to understand physically this last result, so essentially it's the same story of the topological insulator with which you don't have some sort of backscattering, right? Because if you only have potential disorder, this won't flip the pseudospin, right? And you also eliminate the inter-valley scattering, so that you have some, effective conservation of the pseudospin, right?
So which one are we called pseudospin? Really,
AB sub lattice. Right, it's playing the role of spin in this case because you have only disorder in the sigma zero in the unity, right?
Right.
So the disorder is not doing this spin flip, if you wish.
Yeah, but spin is not conserved in this area. It's pure spin.
Right, I'm just trying to understand it physically. So it's essentially the same story of the topological.
It's the same story, yeah. So this one corresponds to surface of a 3D topological instrument. Yeah. Yeah, and so this, on a sigma model language, this is a reason for manifestation of topological protection. So, but I think we should stop here and let's talk about this next tomorrow.